Welcome back to our course on radio astronomy. Let's start with a quick review. In the 1930s, scientists discovered that there were objects in interstellar space that emitted radio waves. We looked at two ways to make radio waves. The first from thermal emission, that's the kind that a material object radiates naturally to its surroundings. The second radio source is non-thermal emission from cosmic rays interacting with magnetic fields. It's interesting that the pioneers of radio astronomy first discovered non-thermal emission before anyone even knew that such stuff should exist. Thermal emission from the sun and planets was not detected until some years later. So far, we've spent time with Carl Jansky and Grote Reber in the United States, and with Ruby Payne-Scott in Australia. There was radio astronomy activity in England during the years of World War II as well, but now I want to jump the North Sea and land in the Netherlands, where we'll meet a pioneer of radio astronomy who was quite different from all the rest. Instead of coming at radio astronomy from the radio side, he was an actual astronomer. Jan Oort of Leiden University in the Netherlands was one of the most visionary and accomplished astronomers of the 20th century. Among other things, he'd worked out the rotation of the Milky Way, our home galaxy, and deduced the existence of a cloud of comets around the sun that we now call the Oort cloud. When we meet him, however, Oort was out of a job. The German army had invaded the Netherlands in 1940, and their occupation lasted until 1945. They began implementing Nazi policies and demanded that Leiden University purge all faculty of Jewish descent. There were protests. Oort resigned all his positions at the university and moved to a small village. He was out of a job. He didn't stop thinking about astronomy, though, and he arranged some clandestine meetings with other former faculty and students. He learned of Reber's discovery and began thinking about radio astronomy. Oort was keenly interested in the structure and dynamics of the Milky Way, but traditional astronomers had always been frustrated by one obstacle. They could hardly see any of the Milky Way at all. The problem was interstellar dust. Here's how the Milky Way appears from Earth, as a band of stars stretching across the sky. By 1940, astronomers had worked out that our Milky Way is a galaxy like billions of others in the universe. Here are photos of some other galaxies. The one in the upper left is probably not too different from our own. Whenever I use the words the galaxy, I mean our home galaxy, the Milky Way. Galaxies like the Milky Way are concentrations of a few 100 billion stars held together by their mutual gravitational attraction, flattened into a disk and rotating around a common point. Here's a deep look at the central region of a nearby spiral galaxy. But see those dark patches? They are clouds of gas and dust. And by dust, I mean little specks of matter, carbon, silicon, ice. They are less than 1/1000th of a millimeter in size, but are very effective at blocking starlight. From our vantage on Earth, we can see these other galaxies just fine, looking down at them from above. But since we are in the Milky Way, we can only see it edge on. Let's look again at the Milky Way. See these dark patches? Those are dust clouds. And the Milky Way has so much interstellar dust that we can only see a few percent of the stars. The dust blocks the light from the rest. Now, radio waves aren't bothered by a few specks of dust, no matter how well it blocks light. So Oort was thinking about radio astronomy as a way to see through the dust. He was particularly interested in finding a way to use radio astronomy to measure the rotation of the Milky Way. Last lecture, we described the two general kinds of electromagnetic emission: continuous in frequency and discrete. Continuous is just that. The emission constitutes an unbroken continuum across a wide range of frequencies. Discrete is the opposite. Discrete emission occurs only over a very narrow range of frequencies. All man-made sources of radio emission that are used for communication are discrete. They are confined to just a small range of frequencies. Here's our spectrum of thermal and non-thermal emission with a few discrete spectral sources superimposed to show how they would appear. Those red lines represent radio emissions over a narrow range of the spectrum. On the scale of this figure, they look like simple lines, and we call them spectral lines. If we were to zoom in, we could see that many have a very complex structure, but they are still confined to a relatively small frequency range, and we still call them lines. So the two types of radio emission are line and continuum, narrow frequency range, broad frequency range. But here's what's really special about emission from a spectral line. You can do something you can't do with the continuum. You can measure a velocity through the Doppler effect. The Doppler effect is named after the Austrian physicist Christian Doppler, who noticed that waves from an approaching object would be bunched up, and for that reason the distance between peaks would be shorter and the frequency higher. Waves from a receding object would be stretched out, making them longer and at a lower frequency. Now, if you know precisely what frequency a given radio emission should be when it is at rest, its so-called rest frequency, and if you can measure very precisely its observed frequency, you can calculate its velocity toward or away from you. What makes line emission? The answer was known for some time, even in the 1940s. Spectral lines are emitted by atoms and molecules. So we need to know something about atoms and molecules. We need to look down to the quantum level to understand how spectral lines are formed. Although the objects around us appear solid, we know that they're composed of atoms and molecules that have the properties of discrete things. We might also assume that because we can spin something like a baseball at any speed we wish, that rotation is also continuous on all size scales. But it's not. On the atomic and subatomic scales, properties like rotation, vibration, excitation are not continuous at all, but exist in discrete chunks. They are quantized. Let's take a molecular dumbbell made of two atoms, carbon and oxygen. This is the familiar and dangerous molecule, carbon monoxide. We sometimes call it CO. The molecule has a certain angular momentum as it spins, and that angular momentum is quantized. If the molecule is at rest, you can kick it and kick it and kick it, but it won't rotate until you kick it just hard enough to put it into its first excited rotational state. It's like climbing stairs. You have to lift your foot high enough to make it to the next stair. Halfway does you no good at all. A good way to kick a molecule like this into a higher energy state is to hit it with a photon, a bit of electromagnetic radiation with just the right energy. Let me stop for a minute to prevent possible confusion. So far in this course, we've used the word wave to describe the kind of electromagnetic radiation that we study with radio telescopes. It's a very convenient description. But you probably know that electromagnetic radiation, like radio waves and light, also has properties of a particle. That particle is called a photon. It's sometimes easier to visualize the radio signals as a photon, so I'll use that term now and again. But it's always the same thing: electromagnetic radiation that has characteristics of both a wave and a particle. Okay? As I said, a good way to kick a molecule like this into a higher energy state is to hit it with a photon, a bit of electromagnetic radiation at just the right energy. We've taken our carbon monoxide molecule and put it into its first excited rotational state. But let me emphasize the important fact again. There's no way to make the molecule rotate any slower than its first excited state. No way. It is either at rest or rotating in one of many discrete quantized states. This is one of the mysteries and the realities of the quantum world of atoms and molecules. Now, the same is true for molecular vibrations. If you think of the CO molecule as a C and an O joined by a spring, then the vibrational state of that spring is quantized as well. So we've gotten our molecule into what is called an excited state by hitting it with a photon of just the right energy. Well, nature does not like to stay excited, and sooner or later it will revert back to what we call the ground state. And when it does, when it stops rotating, in that process it will emit a photon of the same energy as the photon that put it into the excited state. The process is reversible and symmetric. Absorption of a photon into an excited state, decay of the excited state, and emission of a photon. We call this making a transition from one state to another, and zero rotation is the ground state. Another way of exciting a molecule is through a collision. A collision of just the right energy knocks the molecule into the excited state, and it can come back down by emission of a photon. In this case, kinetic energy, the motion of a particle, is absorbed by the molecule, which then turns that kinetic energy into electromagnetic energy when the rotational state transitions back to the ground state. Individual atoms can also have discrete internal energy states. The hydrogen atom, for example, consists of an electron and a proton. If we hit the hydrogen with just the right energy photon, it will absorb the photon and jump into an excited state, with the electron further from the proton than before. But like our excited carbon monoxide molecule, the excited state will soon decay, emitting a photon of discrete energy. We actually observe this process every day without thinking about it. We call the streetlights that produce yellow light sodium lamps. And we're speaking the truth. The light comes from excited sodium atoms that emit at discrete wavelengths that our eyes see as yellow. The same thing with the red neon lights whose light comes from, ta-da, neon. Xenon is used to make bright lights for automobile headlights. The spectacular color in fireworks comes from specific atoms, all with their discrete energies and their discrete colors. Back to astronomy. The Dutch astronomer Jan Oort had used the Doppler shift of optical spectral lines to determine the rotation of the Milky Way in our part of the galaxy. But Oort wanted to see further, the entire Milky Way. Despite the war, he learned of Reber's work and understood that radio astronomy promised a way to peer through the dust. Oort met with a talented Dutch student named Hendrik van der Hulst and gave him a problem. Using what was then known of the physics of atoms, what common element would produce a spectral line at radio wavelengths? Van der Hulst worked a bit and came back with an answer in 1944. The answer was hydrogen. Hydrogen, the most common element in the universe, in its simplest form as individual atoms, should produce a discrete radio emission line. Now, hydrogen is composed of one electron that you can think of as being in orbit around a proton. Both the electron and proton have a property that we call spin. You can think of both as magnets, and spin gives them a north and south magnetic pole. Now, if you've ever played with simple magnets, you know that it's difficult to force the two similar magnetic poles to face one another. It takes energy. Same with hydrogen. Spin is quantized, so it can be either up or down. That's all. The parallel spin, like two magnets with their poles aligned, wants to decay, like a magnet wants to flip, into anti-parallel spin. When it does, it will emit a photon that is at a radio frequency of 1420 megahertz. 1420 megahertz is a wavelength of about 21 centimeters. Van der Hulst reported his results at a wartime colloquium in Leiden. A frequency of 1420 megahertz was well within the reach of technology of the mid-1940s. After all, Reber had built a receiver to work at a higher frequency of 3300 megahertz. But the war and the German occupation of the Netherlands made it impossible for Oort's group to try to detect the radio emission, the spectral line of hydrogen with a wavelength of 21 centimeters, before 1945. News of Van der Hulst's prediction of the possible existence of the 21 centimeter spectral line spread after the war, and scientists in the Netherlands, Australia, and the United States started building the equipment to try to detect it. Radio astronomy had taken an interesting turn. Up until that point, the attitude had largely been, let's build something and see what we see. But now there was a goal: detect the theoretically predicted radio emission from neutral atomic hydrogen. But there was a catch. Van der Hulst's calculations also suggested that the line could be too weak to ever detect. The Soviet physicist Joseph Shklovsky was less pessimistic in a paper that he published in 1948, but the truth was that no one knew. Oort was not deterred. He was adamant that the 21 centimeter line from hydrogen had to be there. There were 3 teams working independently. One was led by Oort in the Netherlands, and there was another in Australia, and the third was at Harvard, consisting of Edward Purcell and his graduate student, Harold Irvin Ewan, who went by the name Doc. Oort's group started first, but they did not have the advantage of the enormous technical base built up in the US and Australia during the war. The Dutch effort was also set back by a devastating fire that destroyed much of their equipment in early 1950. So Ewan and Purcell at Harvard made the discovery in 1951. Doc Ewan told the story during a visit to the Green Bank Observatory for the celebration of the 50th anniversary of the discovery. His PhD thesis advisor, Ed Purcell, who later went on to win the Nobel Prize in Physics for something completely different, was not at all convinced that the 21-centimeter radio line from hydrogen could be detected. Although the search would be the basis for Ewan's PhD thesis, Purcell suspected that they'd get a negative result, only a limit on the brightness of the 21-centimeter emission, not a real detection, kind of like Reber's first measurements. They built what's called a horn antenna, and here it is sticking out of a fourth-floor lab window of the physics building at Harvard, with Doc Ewan, the graduate student, peering into it. A horn antenna is simply something to catch and concentrate radio waves, exactly like a funnel. To their surprise, Ewan and Purcell got a signal. The radio waves from hydrogen had been found exactly at the predicted frequency, 1420 megahertz, at a wavelength of 21 centimeters. Ewan and Purcell spread the word, and within a short time, the groups in the Netherlands and Australia confirmed the discovery. But here's the extraordinary thing. Ewan and Purcell decided to delay publication of their discovery until the two other groups had confirmed it, so that all three could have their papers appear simultaneously in the same issue of the science journal Nature. It was a great moment for radio astronomy, and it transformed the field. This was the first spectral line observable at radio wavelengths, and it remained the only radio line for more than a decade. Ewan and Purcell went on to other work, but Oort's group and researchers in Australia started systematic studies and began mapping the hydrogen in the Milky Way. Here's an image of the hydrogen emission from the Milky Way over the entire sky. I put this together more than 25 years ago, and we'll see more modern, more detailed images in a later lecture. But let's notice a few things for now. The figure is oriented so that the Milky Way is horizontal. It's the bright band running across the center. Most of the hydrogen in our galaxy lies in a fairly thin layer held down by the gravitational attraction of the stars in the Milky Way. It's the same reason that the Earth's atmosphere hugs the surface: gravity. But there is also hydrogen in every direction we look. I spent some time a few years before this figure was made trying to find a hole in galactic hydrogen, some direction in the sky where there would be no galactic hydrogen whatever, but struck out. Galactic hydrogen is everywhere. The large loops that we see in hydrogen come from clusters of supernovae, stars that have exploded. The explosion blows big bubbles in interstellar gas and sweeps up shells of hydrogen. We saw some of the same loops in the non-thermal continuum map. We can also see something different in the lower right. Those circular dark streaks are defects in the data, problems with the measurements. Now, we've gotten better measurements since then, but I wanted to show the data as they appeared in 1990, because try as we might, our measurements will never be perfect. We always need to be alert to possible problems in the data, and it's our duty as astronomers to distinguish the problem from the discovery. We're going to leave the 21-centimeter line for now and return to it in later lectures. But I can't leave the topic without passing along something that Doc Ewan said during his visit to the Green Bank Observatory 50 years after his discovery. I already mentioned that his advisor, Ed Purcell, was convinced that they would not detect a signal. Purcell told Ewan that a negative result would have to be extremely precise to be worthy of a PhD thesis. So Ewan worked hard to make his receiver as sensitive and stable as possible. But before long, the news spread among the Harvard faculty that this experiment was unlikely to come up with a real result. One winter day, Ewan was coming back from lunch, and, as he told it, he saw a gang of junior faculty from the Harvard physics department trying to throw snowballs up into his horn antenna. As he put it, quote, "The faculty could smell a failed experiment a mile away." Ewan also said that had he and Purcell known that the Dutch were trying to detect the line, they would not have bothered. It's amazing how some things turn out. Here's a photo of Ewan 50 years after the detection, standing next to his original horn antenna. This was taken at the Green Bank Observatory during the celebrations of the 50th anniversary. The horn is there today, and if you visit, you can walk right up to it. So far, I've emphasized the use of radio spectral lines to measure velocity through the Doppler shift. But the spectral lines also give us additional information. In many cases, the strength of the emission tells us how much hydrogen there is. This is kind of obvious, isn't it? The more stuff you have, the brighter its emission should be. Here's an example. This is an enormous cloud of hydrogen that we call the Smith cloud. It appears to be on a collision course with the Milky Way. The colors here are totally arbitrary and were chosen just to show off some of the features of this amazing object. We'll spend some time with the Smith cloud in a later lecture. For now, I just want to make the point that from measurement of the 21 centimeter line, we can determine that in the location marked by an X, we are seeing emission from 5 times 10 to the 20 hydrogen atoms per square centimeter. Here's how we figure this out. This drawing shows an imaginary cloud of gas filled with atoms. The atoms radiate in all directions. We say that the emission is isotropic because it doesn't have a preferred direction. For atoms like hydrogen undergoing spontaneous emission of a radio wave photon, the emission is isotropic and can go in any old direction. It's obvious that the signals from only a small fraction of the hydrogen atoms will end up being captured by the radio telescope on Earth. But if the emission is truly isotropic, we can correct for that exactly. Next, we have to consider if a radio wave from the back of the cloud can make it all the way through the cloud without being absorbed. In our discussion of quantized angular momentum states of the carbon monoxide molecule, C+O, we talked about the molecular dumbbell being excited into a rotational state by being hit by a photon of the right energy. So this here photon is merrily making its way toward our radio telescope on Earth when, wham, it hits a CO molecule, and since the photon has just the right energy, it's absorbed by the CO molecule, which then goes into an excited state. Sometime later, the excited state decays, emitting a photon, but the emission is isotropic. That is, the photon can come out in an arbitrary direction. The entire process has removed a photon that was heading toward us and essentially scattered it towards some other part of the sky. If we want to actually count the atoms in a cloud from the emission we detect, we need to know how often this happens. How often does a photon from the back of our cloud hit something on its way toward us? It's a question of transparency, really. If the cloud were totally transparent to photons of a given energy, then anything starting at the back of the cloud would make it out to our telescope. If it were totally opaque, nothing from out the back would make it out. We've already discussed the case of an object that's totally opaque. It's a black body. A black body emits only from its surface. It does not matter how much stuff there is behind the surface. The radiation from that stuff never makes it out. A black body is as perfect in its opacity as a totally clear object is in its transparency. Back to the Smith cloud. We believe that it's nearly completely transparent at the frequency of the 21 centimeter hydrogen line, so we can count every atom. We really can. We can count every hydrogen atom in the Smith cloud, even though it's halfway across the Milky Way. And now back to history. For more than a dozen years, the 21 centimeter line from hydrogen was the only spectral line known at radio wavelengths. Then, in 1963, emission lines of the molecule OH were detected around 18 centimeters wavelength. They come at a bit shorter wavelength, a bit higher frequency than the 21 centimeter wavelength of the hydrogen line. Well, the obvious next step is more complex molecules, combinations of atoms into larger groups. But here radio astronomy took a different turn and a detour of several years. Measurement of spectral lines at optical wavelengths showed that there were diatomic molecules in interstellar space, molecules made of two atoms. These were simple molecules like CH and CN. Could molecules like this have transitions in the radio? And could there be more complex molecules out there? Well, you have to understand that interstellar space can be a harsh environment. Our sun constantly bombards Earth with ultraviolet photons, X-rays, energetic particles, nasty stuff that's deflected by Earth's magnetic field or absorbed by our atmosphere. It would fry us otherwise. Let's all be thankful for a moment, just for that. But the environment around Earth is sweet compared to interstellar space. where there's much more ultraviolet radiation from stars more massive than the sun. We all know that UV radiation is bad for the skin, and that's because it's energetic enough to break down the molecules in the cells of our skin. In general, molecules are rather fragile. So the theory in the mid-1960s was that complex molecules like water, for example, would not exist in interstellar space in any significant amounts. They would be destroyed by the general radiation field from stars. The interstellar medium should be limited to 2 atom molecules, nothing more complex. Then came Charles Townes. Charles Townes already had a Nobel Prize for work that ultimately led to the development of lasers, and he had turned his mind to radio astronomy. Using a relatively small antenna at the University of California's Berkeley Radio Observatory at Hat Creek, he and fellow researchers detected the telltale emissions from interstellar ammonia molecules at the frequency of 22 gigahertz, that is, 22,000 megahertz, a wavelength of just over 1 centimeter. Wow. They soon added interstellar water to their list of detections. Good old H2O in interstellar space. That opened the floodgates. Carbon monoxide, formaldehyde, acetic acid, and on. Here are models of just a few of the molecules we've discovered through their radio emission. The universe is a lot more protective of its molecules than we ever expected. We now know that dark clouds, which are found throughout the Milky Way, are excellent nurseries for the growth of complex interstellar molecules, complex organic interstellar molecules. There are now about 150 molecular species that have been detected in interstellar space through their discrete emission at radio frequencies. We can measure their velocity using the Doppler shift, and from the intensity of their lines, determine the number of molecules in places far from Earth. With the discovery of radio emission from interstellar molecules, radio astronomy suddenly became of interest to chemists and biologists. Did the complex molecules that form the basis of life originate in space and seed the Earth? The ability to detect discrete emission lines from atoms and molecules at radio frequencies is a tool of incredible power, and astronomers use it every day. Thank you.